Right, so you ready?
Ready, Freddy?
Sick. Okay, cool. So we're going to look at image compression today. Moved on from audio. So audio is kind of, the reason we started with audio is it kind of gives us an introduction to those lossy concepts that we talked about, all the lossy stuff, you know, Huffman and Limpel-Ziv and all that kind of stuff. And that starts us off, and you know, it's used in all compression systems. We'll see it again in just a moment here, to be honest. And then we're going to start looking at images. Now, images are slightly more complex. We'll start simpler. Then next week, we're going to look at JPEG, which is a more complicated system. And then after that, we're going to start looking at video, which is like image compression, and then a whole bunch of other stuff in order to make video more compressed as well. So obviously that gets more and more complicated as we go through. But we're starting off moderately simple here. Like, none of this is particularly simple, don't get me wrong. But you know, it is what it is. So we're going to start to look at ways in which we can compress images. And the first thing we're going to look at this time is something called PNG. You've probably come across PNG files before. So it's a good starting point for us. Portable network graphics is what they're called. But before we get there, we haven't really spent enough time, in my opinion here, really talking about the difference between raster and vector graphics. We touched on it in the first lecture of the whole thing, I think. And then we didn't really sort of mention it again. And so we're going to look at that as the first port of call today. There will be, on the seminar bit, the first bit is just looking at some vector graphics. Now, we kind of know that, you know, raster graphics are made up of little bits and bobs, pixels, basically. And so we string those pixels out in rows and columns, and then we turn that into an image. That's fine, but if you think about the compression struggle, the thing we have to do with that compression, that's quite difficult. We've got to take each one of those pixel values. Each one of them is going to have a red, green, and a blue value. We then have to think of ways that we can compress that and find redundancies in that, and that can be quite difficult. The negative side of raster graphics is obviously that pixels have a limited resolution. If we have an image, we can have a certain resolution of image. If we zoom in and out on that image, it gets bigger, but it also starts to look pixelated. We've seen this, haven't we? We all know this stuff. When you zoom in or drag, you know, resize an image, if it's a raster image, it looks blocky and terrible because there's a limited resolution. The great thing about vector graphics is they are an unlimited resolution. They are a resolution they are a style of image that's made up of rules, basically. We define a whole bunch of mathematical rules, and that allows us to zoom in and zoom out kind of indefinitely, which is cool. That's a really useful attribute. So that's quite a useful thing. And here is one, by the way. That's an SVG, scalable vector graphic. It's a good example because it's moderately complex. Obviously, it's not super complex, but there's some complexity to it. And it has gradients and that kind of stuff. And it's actually made up of this. So this is the actual vector graphic information. And we'll look at this in a minute in the seminar session as the first thing. So you can see here you've got gradients. There's like linear gradient. And it, actually down here is where all the paths are drawn. I probably should have scrolled down. Gives its width and its height, the version of the actual file itself, the size of the view box, which is how big it is, and it does define those things in pixels, kind of ironically. And then it talks about some other parts and bits and bobs here. You know, the schema of this thing is all built from something called XML, which is a generic language that you can build all kinds of different bits and bobs in programming in, but we can make images with it. Now, again, huge advantages of this. This is just a text file. We can compress this using normal text compression methods, which are very cheap and very fast and pretty decent compression. And so these things are tiny. Like SVG files are very, very small. We don't have to think about individual pixels for every single part of that image. We just define a whole bunch of rules, a whole bunch of paths, and we use things called Bezier curves. So there's maths that basically can define the shape and the kind of ballistics of a curve. And so you can use that to plot this thing out and basically build it out of curves. You may have done it with programs like Illustrator. I'm not sure what we have on the computers here, so we're going to have a look in a minute. So great advantages, the fact that they're very small. They're very clean. You can zoom in and out of them indefinitely, as I've said. But the other thing, from a programmer's point of view, one of the great things about this is it's text. And if you're a programmer designing something like a website, this is a text file that you can version control just like all the rest of your text files. So if I'm building a website, all the files go up to something like GitHub, And you version control them, which means that if I make a change, you can track those changes. You can see who's done those changes. You can roll back changes, and you can have different branches of your development. So you can have like an experimental branch where you do crazy stuff and hope that it works together and then merge it in when it works. And you can actually version control all of this. From a programmer's point of view, that's actually really useful. Like being able to say, oh, I changed the color a bit. Do we like it? This line is slightly different, whatever. So they're really quite cool. So we'll have a look at those as the first thing we do today. But the main topic of what we're going to look at today is PNG, which again is both of the formats we've just discussed there. Not all vectors as a concept, but SVGs, scalable vector graphics, were designed for web. And PNGs are designed for web, portable network in the name, kind of gives that away. So PNGs are designed to be web-based. And we've looked at some of the compression systems. And this can make some sense because we've looked at this already. But one of the things that we've not really seen before, but is kind of obvious to do, is something called run length encoding. So if we're going to take an image and we have a bunch of stuff that's all in a row, it's really easy for us to say, right, well, this is the pixel value, and then just have it for the next however many pixels. So I've given this as the example. This is a nice clear example. If you have this part of the G, for instance, in the Google logo, you've got a whole bunch of pixels in a row, and you just say this one's white, and then for 36 pixels, it's white. It's nice and simple. This looks a bit blurry because we've zoomed in, and the anti-aliasing of the machine is trying to kick in and make it not look blocky. But if you think, in a graphics package, that should just look like blocky pixels. So that's quite good. That gives us a redundancy within the image that allows us to compress. So we can compress a huge amount there. If we've got one pixel that we're defining and a whole bunch of them in a row, then we're compressing by however long that length is, and that's called run length encoding. So we say this pixel again and again for however many pixels there are. That's great. Now the big flaw in that is photos. So obviously photos have fine gradients, they've got detail, they've got bits and bobs that kind of carry on after. There's all kinds of stuff here. It's not like this. There's not a lot here that is run length encodable. And so that's a major flaw in this type of encoding. So PNGs are very often used for logos and things like that. This thing, making photos look better, is the job of another kind of a codec we'll look at next week. JPEG is better at it, basically. So that's something we can do. Now, this is a weird image I've chosen here. There's a specific reason for that, and I've given some notes in it in the lecture if you want to download it. Basically, there was this thing early on in this world where they used like a female Playboy model for all of this compression stuff. And there's a big kickback against that because that's a weird thing to do in isolation. And there's a lot of people sort of saying that you shouldn't use that image now because it's kind of offensive to people coming into the industry that are female. So I've used a piece of the image in order to highlight that, but not the whole image. You can see it if you want to. It's in the notes. So the two compression methods we've got is run length encoding. That's relatively new to us. We've not seen that, but it's obviously kind of obvious. It's also kind of obvious, sorry. And the other one is Limpel-Ziv. Remember that one? Remember that bit? Not that I'm testing, but has anyone got any remembrance of that thing? Remember what Limpel-Ziv was doing a couple of weeks ago?
No, I remember it, but not enough to try and call back on it right now.
Okay. So PNG uses I've not detailed it here. There's loads of detail in all of this that I'm kind of glossing over, as we always do with these modules, and I kind of always make that complaint. So it uses a modified version of Limpel-Ziv, and LZ compression is a dictionary compression. So if you remember the idea that you make a dictionary up of a bunch of common stuff. So one of the major flaws of this is that if I had a simple repeating pattern, then you don't have any run length. But a simple repeating pattern is very nicely compressed by dictionary compression, because you just say all of that pattern, it repeats 56 times in a row, we'll just call that this particular small short code, and off you go. And it's also, I've not actually written it now that I think about it, it's also Huffman encoded as well. So you remember the Huffman tree thing that we looked at? It also has that. So those are our compression schemes. So that's all we have as an arsenal of compression in PNG. And you might think, well, that's fine, but that's not actually particularly strong. We can compress text files that way. We can compress anything that way, really. It's a very basic compression scheme. And so it doesn't really meet our demands being specific to images. And so we've come across an issue immediately with this set of pixels here. You can see that there's no run length because they're all different as they go along, and there's no repeating pattern. So dictionary compression sucks. And the same thing with the other one. Huffman codes are not going to be particularly good here. If you convert all these into ones and zeros, there might be some patterns of ones and zeros that we can exploit, but you know, it's sorry, no worries. And so Huffman codes and all of the compression systems we've come across up until now aren't going to be very useful to us. So we've got those compression systems, and we've got data that doesn't really fit that. Now, there's two ways of solving such a problem. If you've got a new problem that's hard to solve, you can either make a new solution for it, so come up with a brand new compression scheme, and it turns out that's really kind of freaking hard to do. Or you can reimagine the problem that you're looking at. So here you can see that we do have a gradient pattern, and this example was borrowed from a really illustrative YouTube video, actually, which I'll put in, I think it's linked here in the notes. But there's clearly a pattern here. It goes from dark here, it goes a little bit brighter this side, and it gets a lot brighter as you go down, and so there's a gradient, you know, it's a gradient pattern. You think, well, this must be compressible somehow. How do we make that happen? And the way that PNG does it is via something called transforms, which it calls filters. So there is a pattern here that you can see, and if we think about it for a little while, we can see that there is an observable pattern. So basically, in this particular gradient, it's +4, +4, +4, +4, +4 in that direction, and as you come down, it's +32 each time. So there's a nice mathematical relationship there, an easily definable pattern. So what we're trying to do with these transforms is to transform our hard to compress image data that doesn't fit our nice compression schemes into something more compressible, basically. So it's like a middle ground. It's a middle step between our idealized data and the compression schemes that actually work really well that we know of. So in this example, we can say that it's +4 whenever you go to the right. Now, I've not determined the relationship up and down, and there's a reason for that. We'll see that in just a second. But basically speaking, if you hard-coded this entire pixel here as number 32, then you can code the next guy along just as a +4 relationship all the time. And then before you know it, this is a run length. You can just say, well, keep +ing 4. And that run length then becomes compressible. So we've transformed our image into something that is essentially more compressible. And the advantage of that, again, is run lengths and things like that, things that we're trying to tease out of our image, but it's also that we're using smaller numbers. You know, those difference values can be smaller. So here we're just using the number 4 instead of a full range of 8 bits, which is up to 256. So that is an example of a transform. Now, PNG, Portable Network Graphics, that particular standard, it's not particularly important to us, but it's a good illustration of what we're looking at in the next couple of weeks, has 5 transform types. 4, really. The transform types themselves are those on the board there. It says none, so you just do nothing to it. So if you've got a really nice run length already, you don't want to fuck that up, you just want to keep it. So you just do nothing to it, that's perfectly fine. Then you've got sub, up, average, and path, which is a weird name. So PNG, as a standard, makes a choice for each of the scan lines, each of the lines of data, each of the rows of pixels, as to which one of these it chooses. So it makes a choice for every single one. So you can have a PNG file that has a different transform for each line. So whichever one works best, it will run, basically. And that's how it finds the best way to transform each of those lines and therefore give you the best compression. So the first one is the sub filter, and that's the example I gave before, basically. It looks to the pixel on the left, and it just gives a difference value. So it looks to the left and says, what's the difference between that one and this one? What's the difference between that one and this one? That one and this one. And so you're continuously going through and saying, right, well, if that one's 36 here, then that one will be 4 more, that'd be 4 more, that'd be 4 more. And it allows you to kind of have these small numbers. The idea of this is you're relying on a redundancy of similar pixels, basically. You're always, or a lot of the time in images, you're either going to have like big changes, like logos and stuff like that, which will give you nice run lengths, so you get good compression anyway. Or you get things like gradients, you get things that are like linearly falling off in some direction, or you get stuff that fades in alpha channels or whatever. And so you end up with small differences between the pixels next to them. So this is a way of doing that. It's called the subfilter. It's just look to the left pixel and see what the relationship is. Next one's just as easy, one called the up filter. You wouldn't be surprised that it just goes up a pixel. So this is exactly the same filter, but it looks up instead. So this would code nicely things where you've got similar pixels to the row above. Next one is an average filter. I've been lazy and not bothered to give the example here because it involves working out averages. But you're looking at the pixels above and to the left and then displaying the average. So if we say that pixel there and that pixel there, well, what's the average? Put it there. And that, again, different types of images might result in a sharper or more compressed image type, or it gives you run lengths and all that kind of stuff we talked about. Run lengths and patterns are what we're after, basically. So the average filter might come up well. And then there's the slightly more complex one called the Path filter. Now this one, again, this is all a bit 11 herbs and spices, like a lot of this stuff tends to be. You calculate a value, basically, a base value. This is an incorrect example, I forgot to remove this. So the base value basically is you take the upper, so say I'm looking at this pixel here, you look at the number above, you look at the number to the left, you add them together, and then you minus that one, the one that's to the up and left. Again, who knows why? I mean, this stuff is statistically tested, and that's about all we do, really. We throw a bunch of images at it and make sure it works, and if it does, then great. If you want to come up with any better examples that work better than this, then I'm sure the world would appreciate them. But this is where we are. So, yeah, you make this base value, and then what it does is it looks at the pixels around the, it looks at its target pixel, and it says, right, what's the difference between the base value that we've done, the up, left, and up, left, and then it just defines one of those and gives a difference from that to this. So it's like a bit of a strange kind of transform. I'm not sure why that's a good idea, really. I can't really envision why that's a good idea. But I guess it's like a smoothing kind of averaging thing, and it probably works for certain gradients and things like that. Again, this is all empirical, not mathematically accurate, as it were. And in all the filters that we talked about, the sub, the average, the up, and the path, if it's looking at a pixel that's around the edge, so if you're looking at this one or this one, and it's trying to look left, it just takes that number to be 0. So if it's looking at a left that doesn't exist, it takes that number to be 0 and carries on. It does the maths exactly the same. So each of the RGB values that you get are all treated separately. So you can have, for instance, an RGB value for a pixel and the one next to it, and all of the R values might be differently coded to all of the G values, so all of the greens or whatever. So you might have an image that is mostly red in a certain area, for instance, and that means that there's a really decent run length on green already because there's hardly any green there, for instance. And so the line for those particular RG and B values can be coded separately. So that's a nice efficiency that comes out of PNG. And each of the lines can be, as I've said already, can be coded separately as well. So as you go down the rows of the image, in all of the separate channels, you can select these filters. So you're selecting path because it's the best for that one, and then you're selecting up because it's the best for that one, or none, or whatever you happen to select. Now that obviously gives us a huge challenge, right? You have to come up with a way of choosing those. And one of the big difficulties of that is if you went through and tested every single line of pixels for every single channel of color for every single transform that you want to run, there's billions there for any image that you're doing, there'll be billions and billions and billions of these transforms to do. So what they do instead is a thing called sum of absolute difference, which is a really cheesy kind of a thing we call a heuristic. A heuristic is something where you calculate a value that seems to have a relationship to the value you care about. So a heuristic might be that, what's a good example? Perhaps your phone detects when you're, well, in fact, your phone detects when you're walking along and it increments steps. There's a heuristic involved in that. It's not detecting your actual steps, it's detecting the heuristic of your phone shaking in a particular way. And it just happens to correlate nicely to the steps you're taking. So heuristics are kind of like that. They're not perfectly accurate, but if you measure a whole bunch of it and grab a reasonably decent heuristic to the thing you're looking for, then you can pretty much measure the thing you're looking for. So you measure this thing called the sum of absolute difference for a particular line, and each of those values will fall into, it will point to a specific one of our filters. And the reason I'm detailing this in particular is because this thing is not mathematically perfectly related. Like I say, it's a heuristic. So there might be a way in which you could come up with a better metric for this that's better than sum of absolute difference. And it might give a better result, but we just haven't been able to do that. No one's done that yet. I think there are a couple of examples of research papers with some in there that are a little bit better. But you know, PNG is about 40 years old, I think, at this point. So it's worked quite well up until now. So you calculate that metric for every scan line, for every filter, and for every one of that RGB channels. So there's loads and loads and loads of that to do. That's quite a lot of processing. So PNG as a type, as an image type, is actually quite computationally expensive. So we are getting pretty decent compression. You know, the compression we're dealing with here is relatively good. It's designed to be networkable, so the idea is that it's designed to be nice and efficient for the internet, essentially. But it's computationally expensive, both to package and unpackage. It's more computationally expensive to compress than it is to decompress, because you have to run all this to work out what the best transforms are going to be. On the way out, you're just told what they are, and then you decompress it. Okay? Now, I've said all that stuff. What kind of, in terms of lossy and lossless, what do you think this is? So PNGs are a lossless image file format. All of those things that I've talked about, all this stuff, you are getting back to perfect integers to the thing you started with. So you're not losing any data. You can decompress this stuff and get back to where you started again. It's just all of these filters are the magic that gets you into image world that makes it more efficient for images in particular, basically. So it's really quite good. Now, the reason I mentioned that as a point is if it always drives me kind of nuts when you have people that are generating diagrams and images and stuff for the web. PNG is a brilliant way of doing that. It compresses very well because you've got lots of run lengths for blank bits and lines and diagram stuff, clear stuff, text and all that kind of stuff compresses really well in PNG. Instead of using JPEG, basically. And next week, like I say, we're going to dive into JPEG. It's a lot more complex and there's a bunch more maths that goes into it. But we'll get into that and see why it's not quite so good for diagrams and things like that. So if you're doing diagrams, things with clean lines and images and things like that, PNG is perfect for it. Logos are great. Like I said, logos and diagrams, that kind of thing. Photos, JPEG. Yeah, that's like the main message, really. Like I say, it always winds me up. People use JPEG for everything, and JPEG is actually not great for a lot of things that people use it for. And then finally, there is another thing that PNG and other image file formats do that we're going to demonstrate again today in the seminar. There's something called progressive images as well. Now, progressive are image file format tags, basically, that allow you to reconstruct the image in a different order. Now, we've talked about PNG going through rows of data, so individual rows. But when you're on the web and you're on a slow connection, that means that you start in the top left corner and you decode these rows one by one by one by one. Have you ever seen it? Well, you almost certainly have, but maybe not noticed. When you are downloading an image and it's taken ages and it comes from the top down to the bottom. Well, progressive images reorders this. You can say, I want that first, I want that second, I want that third. And so you can interlace that and basically get half the resolution at twice the speed. So you half the resolution, run through the rows quicker. What it will do when it's decoding it and trying to show you the image is it will just paste that down. So row 1 will become row 1 and 2, and your image will be half the resolution in the vertical direction. Or more. You can do 3 rows or 4 rows or whatever. Then what it will do is, as it's continuing to decode that image, get the data and decode it, it will come through and fill these lines in. So if you did 3 lines, it will fill the second line in and you get a bit more resolution. If you did 3 lines, and then once it gets to the third line, it will come through and do that. I've given a demonstration of that on the Sol page, that there's a very specific way you need to open it. So you can't just look at it straight away. We're going to limit the browser's download speed, basically, for that particular site, and then try and open it, and you'll see the difference in how they load. The first one will load slowly from the top down, and it'll be really kind of painful. And the second one will go bam through the whole thing really quickly, but it'll be a lower image quality, and then it'll come back through and like rejig the quality. Now, I did that with a JPEG, to be honest. I haven't actually used PNG as a standard because the demonstration is a bit easier, but it's the same concept. So progressive images, if you get that tick box, it's just the different ordering of the lines. If it's on your machine locally, you're probably not even going to notice a difference because it'll be so fast. But it's usually when you're sending things across slow connections and things like that. Cool. That's my face.